Hello learners, welcome back. In today's session, we will be exploring an innovative construction technique, that is precast construction. Precast construction is revolutionizing the industry with its efficiency, quality and sustainability. In this session, we will delve into the various aspects of precast construction, including its advantage, processes and applications in modern construction projects. Now, let us introduce what is precast construction. It is a method of creating a structural component in a controlled factory environment before they are transported to and assembled at the construction site. This technique ensures high quality as the production process is not influenced by external factors like weather, site conditions or variability in labor skills. For example, just imagine you are baking a cake. In precast construction, it is as if you bake the cake in a professional kitchen with perfect conditions, ensuring the best results and then transport it to the party venue. This contrasts with the baking at the venue where your condition might not be ideal. So, let us discuss some key characteristics of this precast construction. First one is factory production. So, producing components in a factory ensures uniformity and precision. Every element from large beams to small panels is made with the same high standards. The controlled environment also allows for the use of advanced techniques and materials that might not be feasible on site. For example, think of a car factory where every vehicle comes off the line identical, thanks to precise machinery and quality control processes. Precast construction offers similar type of consistency. Next is standardization. Precast construction allows for the mass production of components. Standardization leads to efficiency and cost saving, as the same molds can be reused for multiple projects, reducing both material waste and production time. Its real world application could be, for example, in large housing development, the same wall panels and floor slabs can be used repeatedly, speeding up the construction and reducing cost. Next characteristic is speed. So, because the components are made in advance, on-site construction time is drastically reduced. This is particularly advantageous in projects where time is a critical factor, such as in urban developments where delays can lead to significant financial loss. For example, in emergency housing projects after natural disasters, precast construction allows for rapid assembly of homes, providing shelter to those in need far more quickly than traditional methods. Now, let us have a comparison with cast in place construction with the precast construction. Basically, cast in place construction involves pouring and curing concrete directly at the site, which can be slow and labor intensive process. This method is often subjected to delays due to weather conditions, especially rain, which can wash away freshly poured concrete or cause delays in curing. What will be its real world impact? Construction can be halted altogether in cold climates if the temperature drops too low, as concrete will not cure properly in freezing conditions. In contrast, whereas precast elements are manufactured in a controlled environment where curing and setting are not subjected to such variables. This leads to faster assembly on site, as components simply need to be placed and connected. So, there is one question: can anyone think of project in any one city where construction was delayed due to weather? So, how might precast construction have helped avoid these delays? So, think upon it. Now, moving on, let us have a detailed discussion on both the precast construction and construction in place, cast in place construction. First is the production environment. So, in precast construction, there is factory control environment. So, advantage of it is that in a controlled factory environment leading to high quality consistent products, the factory setting allows for precise control over temperature, humidity and other conditions, ensuring optimal curing and strength. This control reduces the variability and unpredictability often encountered on construction sites, leading to fewer defects and higher quality outcomes. Example, precast beams and slabs can be manufactured during any season without concern for adverse weather conditions. Whereas in cast in place construction, that is on-site construction, it involves pouring and curing concrete directly at the construction site, where environmental factors like temperature, humidity and weather conditions can affect the quality of concrete. Risk may include that adverse weather condition, example rain, extreme temperatures, can delay the project, lead to poor curing and potentially result in weaker structure. For example, during winter, concrete may require heating blankets or admixtures to ensure proper curing, adding complexity and cost. Next is about construction speed. So, in precast elements are pre-made and ready for installation upon arrival at the site, drastically reducing on-site construction time. The parallel production process, where elements are produced while site preparation is underway, also speeds up overall project timelines. This method is ideal for impact projects with tight deadlines or in urban areas where construction time must be minimized to reduce disruption. For example, in large scale commercial project, entire floors can be assembled in days rather than weeks using precast slabs and columns. Whereas in cast in place construction, it is a slower process. As you know, this process of setting up of formwork, pouring and curing concrete on site is time consuming. Each stage must be completed before the next can begin, leading to longer project timelines. Each layer or section of the structure must cure properly before additional loads are applied, leading to potential delays. For example, for a multi-story building, each floor must be poured, cured and formwork dismantled before next floor can begin, extending the construction period. Next is the quality control. In precast construction, there is high consistency. The factory environment allows for stringent quality control measures, ensuring that each element meets the required standard. This consistency leads to fewer defects and higher structural reliability. Quality control is easier to manage in a factory setting where conditions are stable and predictable. For example, in precast panels can be produced with exact dimension, smooth surfaces and integrated finishes, reducing the need for on-site corrections. Whereas in cast in place construction, there is variable quality. Quality control is more challenging in on-site due to varying environmental conditions, potential error in formwork and difficulties in ensuring uniform mixing and curing of concrete. Risk could be inconsistent conditions can lead to variability in strength, finish and durability of the structure. For example, in cast in place construction, poor mixing of concrete or inadequate compaction can lead to weak spots or honeycombing, requiring expensive repairs or compromising the structure. Next is the cost consideration. So, in precast construction, as the quality is high and it is taking less time, it is higher upfront cost and lower long term cost. Initial investment, that is the initial cost for precast construction, can be higher due to expense of mold, transportation and specialized equipment. However, these costs are offset by faster construction times and reduced labor cost. If we take the economy scale, for large project, the cost per unit decreases as the number of repeated element increases, making it as cost effective. For example, if you take an example, in a large housing development, the cost of producing thousands of identical precast panels is significantly lower than casting them in individually on site. Whereas in cast in place construction, as you know, it will be of lower upfront cost, potentially higher longer term cost. If we talk about initial saving, cast in place construction typically has lower upfront cost because it does not require specialized mold or transportation of large element. However, the longer construction time and the potential for higher labor cost can make it more expensive in the longer run. Talking about the cost can escalate if there are delays, quality issues or additional labor is needed to correct these defects. For example, in a small custom project, cast in place construction might be more cost effective since there are fewer economies of scale and customization is easier. Moving on to the design flexibility, in precast construction there is limited flexibility. Standardization, because of standardization, that is in precast elements are often standardized, making them ideal for projects that require repetition, but limiting flexibility in design changes once production has started. Customization is possible, but can be costly and time consuming due to the need for unique molds or special handling. For example, in a modular office building, standard precast panels can be used efficiently, but adding custom features like curved walls or unique architectural details can increase cost. Moving on to durability and performance, in precast construction there is higher durability. Precast construction is often more durable due to the controlled manufacturing process, which ensures proper curing and quality. The use of high performance materials and admixtures in the factory can also enhance durability. In precast, elements are more often resistant to environmental factors such as freeze-thaw cycles, chemical exposure and wear and tear. For example, precast concrete bridge components are often designed to last for decades with minimal maintenance even in harsh environment. Whereas in cast in place construction there is variable durability. The durability of cast in place construction structures can vary based on site condition, quality of material and workmanship. Improper curing or exposure to adverse conditions during construction can compromise the long term performance of the structure. A cast in place construction, for example, sidewalk may develop cracks over time if it was not properly cured or if the mix was not optimized for the local climate. Talking about the labor requirement, in precast construction, skilled labor in factory and less on site is required. Precast construction shifts much of the labor to the factory where skilled workers operate in a controlled environment. This reduces the need for a large workforce on site, lowering labor cost and minimizing risk on site accident. The labor required on site is often more specialized, focusing on the assembly and the connection of precast element rather than the actual construction. For example, a team of workers might assemble an entire precast parking garage in a fraction of the time it would take to cast its place with fewer labors needed on site. Whereas in cast in place construction, high on site labor requirement is there. It requires a large workforce on site for tasks such as formwork installation, concrete pouring, finishing and curing. This can increase labor cost and complexity of the managing a construction site. The need for more on site labor also increases the potential for accident and delays, particularly in complex projects. So, if we take an example, pouring a concrete foundation on site might require a large crew working for several days with the need for continuous supervision and quality control. Moving on to environmental impact, in precast construction there is lower on-site environmental impact, as in precast construction it generates less waste on site and often result in a cleaner, more organized construction site. The controlled factory environment also allows for better management of resources and reduction of waste. In precast element, can be designed for better energy efficiency, including thermal insulation properties, which contribute to the overall sustainability of the building. A precast concrete building might incorporate insulated wall panels that reduces energy consumption and contribute to LEED certification. Whereas in cast in place construction, there is higher environmental impact. Cast in place construction typically has a larger environmental footprint due to the on-site mixing of concrete, the extensive use of formwork and the potential for waste and pollution. The need for on-site materials, water and energy can increase environmental impact, particularly in large or complex projects. So, a cast in place construction project might require the delivery and the storage of large quantities of cement, sand and aggregate on site, contributing to dust, noise and disruption in urban areas. Now, let us move on to history and evolution of precast construction. So, if we talk about the early use, the concept of precast construction can be traced back to ancient civilization. The Romans, for example, used modular stone blocks to build structure like aqueducts, bridges and buildings. These early forms of precasting were labor intensive and lacked the precision of modern method, but they laid the groundwork for the development of prefabricated construction techniques. If we talk about the historical insight, the Roman aqueducts, some of which still stand today, were built using large stone blocks that were shaped off site and then transported to the construction location. This allowed for more efficient and durable construction compared to simply stacking stone on site. If we move on to the 19th century, the 19th century saw the introduction of reinforced concrete, composite material that combines concrete compressive strength with steel's tensile strength. This innovation revolutionized construction, making it possible to create stronger, more durable structures. Reinforced concrete was particularly well suited to precasting, as it allowed for a creation of large complex elements that could be transported and assembled on site. So, there is a technological leap. For example, the Eiffel Tower, while primarily made of iron, symbolizes the era's innovative spirit. Reinforced concrete soon became the material of choice for many large scale projects thanks to its versatility and strength. And coming to 20th century to modern era, the 20th century brought significant advancement in the manufacturing, transportation and material science, all of which contributed to the growth of precast construction. During this time, precast construction became increasingly popular for its efficiency, cost effectiveness and ability to meet the demands of modern architecture. Today, the precast construction is used worldwide in a variety of applications, from residential building to bridges and tunnels. Modern precast elements are often made with high performance materials and advanced manufacturing techniques, allowing for greater precision, strength and durability. If we take a case study, the Burj Khalifa in Dubai, that is the tallest building in the world, as you know, utilized the precast concrete in its construction. The use of precast element contributed to project's rapid completion despite its immense scale and complexity. Moving on to the type of precast elements. If we talk about the structural components form the backbone of any precast construction project. These elements include beams, which are horizontal supports that bear loads across open spaces, columns, which are vertical supports that transfer loads from beams to the foundation, floor slabs, which create the floors and ceiling of a building, and the walls, which can be load bearing or non-load bearing. These components are designed to work together to create a stable and robust structure. For example, beams and columns often form a grid-like framework that support the building's floors and walls. If we talk about the non-structural component, in addition to structural component, precast construction also includes non-structural elements. These components serve functional or aesthetic purpose but do not bear significant load. Common example include staircases, which provide vertical circulation within a building, and cladding panels, which are used to cover the exterior of the building, providing both insulation and a finished appearance. If we take an example, precast staircases are particularly popular in multi-story buildings because they can be manufactured to precise dimension and installed quickly, reducing on-site labor and construction time. Cladding panels, on the other hand, are often designed with aesthetic considerations in mind, offering a range of finishes and textures that can enhance the visual appeal of a building. If we could take a real world application, we can consider the facade of a modern high rise office building. The sleek and uniform exterior might be composed entirely of precast cladding panels, each one designed to fit perfectly with the next. Moving on, talking about the specialized systems. For project with specific structural requirement, specialized precast systems are used. Pre-stressed concrete, for example, is a type of precast concrete in which steel tendons are tensioned before the concrete is cast. Once the concrete hardens, the tendons are released, putting the concrete into compression and allowing it to carry greater loads over longer spans. Talking about the technical insight, pre-stressed concrete is often used in the construction of bridges, where the ability to span long distances without intermediate support is very crucial. We take an example of hollow core slabs of a specialized precast system. These slabs have longitudinal voids which reduce the amount of concrete required while maintaining the slab strength and stiffness. Hollow core slabs are commonly used in floors and roofs of commercial and residential buildings. Why do you think reducing the weight of precast element is important in construction? And consider the implications for transportation, handling, and structure design. Think about it. Moving on, we will see the materials used in precast construction. First, we will talk about concrete. Concrete is the primary material used in precast construction, but the type of concrete used is often different from that used in cast in place construction. Precast concrete is typically a high strength mix designed to meet specific performance criteria such as compressive strength, durability and resistance to environmental factors. To achieve these properties, various admixtures are added to the concrete mix. For instance, silica fume can be added to increase strength and reduce permeability, making the concrete more resistant to water penetration and chemical attack. The choice of concrete mix is critical to the success of precast project, as it must meet the demands of both manufacturing process and the final application. Talking about the example, in regions prone to freeze-thaw cycles, air entraining agents might be added to the mix to create tiny air bubbles, which help prevent cracking when the concrete freezes and expands. Talking about steel reinforcement, it is essential in precast concrete element as it provides the tensile strength that concrete lacks. In traditional reinforced concrete, steel rebars are placed in specific locations within the formwork before the concrete is poured. In precast pre-stressed concrete, steel tendons are tensioned before casting, allowing the concrete to resist tensile forces more effectively. If we talk about the technical insight, the placement and the amount of steel reinforcement are carefully calculated by structural engineers to ensure that the finished component can withstand the load it will encounter during use. This is particularly important in load bearing elements like beams and columns. If we talk about the real world application in high rise building, the steel reinforcement in precast floor slab is designed to support not only the weight of the slab itself, but also the weight of occupants, furniture and other live loads. Formwork or mold plays a crucial role in precast construction. The formwork is used to shape the concrete and must be designed to produce components that meet exact specifications. The material used for formwork is often steel or fiberglass, which can withstand repeated use and maintain precise shapes over many cycles. For example, in large projects, formwork might be used 100 or even 1000 of times. So, durability and precision are key considerations. The initial cost of formwork can be high, but its reuse across the multiple projects make it a cost effective solution in the long run. The formwork must also allow for easy removal and the cured concrete without damaging the surface or altering the shape of the component. Moving on to connectors and joints. Connector and joints are essential for assembling precast element on site. These include mechanical connectors such as bolts and dowels, as well as embedded plates and other fittings that allow for the secure attachment of precast component. The design of these connectors is critical to the overall stability and performance of the structure. Its practical application includes that in seismic zones, the design of connectors and joints is particularly important as they must allow for some movement while still maintaining the integrity of the structure. Joints between precast elements must be designed to accommodate movement due to thermal expansion, shrinkage and other factors. Proper joint design also helps to ensure that the assembled structure is watertight and durable. Talking about the manufacturing process, let us discuss. First is the design and engineering. The first step in the precast construction process is the design and engineering phase. Detailed drawing and specifications are created to ensure that each component meets the project structural and aesthetic requirements. These designs take the account factors such as load bearing capacity, thermal performance and ease of assembly. The precision in these designs is vital. Any mistake at this stage can lead to costly errors later on. The use of building information modeling and other advanced design tools is becoming an increasingly common in precast construction, allowing for more accurate and detailed planning. If we take an example, consider a precast parking garage. The design must account for the loads imposed by vehicles, the need for ventilation and the aesthetic appearance of the structure. Each precast element is designed with these factors in mind. Talking about in manufacturing process, second is the mold preparation. Once the design is finalized, the next step is to prepare the mold or formwork that will shape the concrete. These mold must be accurate and durable as they will be used repeatedly to create identical components. The formwork must also allow for easy placement of steel reinforcement and the insertion of any required fittings or connectors. Imagine a large metal mold into which the concrete is poured. Every detail from the position of the steel reinforcement to the smoothness of the surface is meticulously planned. This ensures the final product matches the design specification precisely. Molds can be designed for single use in custom project or for multiple uses in standard components. The choice depends on the scale and the nature of project. Next is in manufacturing process is about reinforcement placement. Steel reinforcement is then placed inside the mold. This step is crucial as the positioning of the steel affects the strength and stability of the final component. The reinforcement is designed to resist the tensile forces that the concrete will encounter during its use. In pre-stressed concrete elements, steel tendons are tensioned before the concrete is poured. This tension is released after the concrete has cured, giving the component additional strength and allowing it to span longer distances without additional support. Reinforcement placement must be precise to ensure that the finished component can carry the design loads. Misplacement can lead to structural weakness or even failure. Next is the concrete casting. Concrete is then poured into the molds. During this process, vibration is often used to remove air pockets and ensure that the concrete fills every part of mold uniformly. This step is crucial to achieving a dense homogeneous concrete structure without voids or weakness. Removing air pocket is crucial because any voids within the structure within the concrete could weaken the structure, leading to potential cracks or failure under load. The concrete used in precast construction is often a high strength mix designed to meet the specific requirement of the project. Admixture may be added to enhance workability, durability and other properties. Next is the curing process. After casting, the concrete must cure to reach its full strength. Curing takes place in a controlled environment where temperature and humidity are carefully monitored to ensure optimal conditions. Proper curing is essential to achieve the desired strength and durability of concrete. Curing is not just about drying the concrete, it is about allowing the chemical reactions that give concrete its strength to occur under ideal conditions. Inadequate curing can result in weaker concrete which may not meet the design specification. In some cases, accelerated curing methods such as steam curing may be used to speed up the process, allowing for faster production times. And next step is the finishing. Once the concrete has cured, the component is removed from the mold and undergoes finishing process. This might include smooth finishing surfaces, adding texture or applying protective coatings. Quality inspection are also conducted to ensure that the component meets all design specifications. For example, for an architectural panel, finishes might include adding a specific texture for applying a color to match the overall design of the building. In structural component, finishes might focus on ensuring a smooth surface that can be easily painted or coated for protection. Quality control at this stage is critical to ensuring that the finished component meets all necessary standards for strength, durability and appearance. Next step and the last step is the storage. Finally, the precast elements are stored in an organized manner to prevent damage before they are transported to the construction site. Proper storage is essential to maintain the quality of the component until they are needed. Component should be stored in a way that prevents deformation, cracking and other damage. Imagine a picture storage of yard filled with neatly stacked precast panels, each one ready to be shipped to its final destination. The components are arranged in a way that makes them easy to access when needed, minimizing delays during the construction process. Storage conditions including protection from the elements and proper support to prevent warping are crucial to ensuring that the precast component remain in good condition until they are installed. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.